Okay, in this video, we're going to learn about acid-base reactions of carboxylic acids. So, carboxylic acids are weak acids because the carboxylic group ionizes only slightly in water to give what we call the carboxylate ion and a proton. So, in other words, H plus with water makes H3O plus, or that proton. Typically, carboxylic acids ionize only to the extent of 1% or less in water. So this is a weak acid. We said they would, dissociate anywhere from, some people say 1 to 3% or 1 to 5%, but 1% is certainly in that weak acid category, especially if they're 1% or less. Also, carboxylic acids with 1 to 5 carbon atoms are soluble in water. And larger carboxylic acids are water insoluble. So what are the big things to remember here? These are weak acids because they ionize 1% or less. If they have 1 to 5 carbon atoms, they can be water soluble. If they are larger, they are water insoluble. So think anything with greater than or equal to 6 carbon. So carbon greater than or equal to 6 is going to be water insoluble. So the small chains are soluble, the larger carbon chains are not. So let's think about it. Our carboxylic acid is our R, C, double bonded to O, and then OH. When it gets together with water, essentially what's going to happen is the hydrogen of the carboxylic acid gets together with water to form H3O plus. That leaves the carboxylate ion negative and the H3O plus positive. So the carboxylate ion is R, C, that's double bonded to O, and then O minus. So that's what we're calling our carboxylate ion. Let me just get a pen color that we can see here and call it the carboxylate ion. Carboxylic acid when it's lost its proton. That's what our carboxylate ion is. Okay, so carboxylic acids will react with bases such as NaOH to form that carboxylate salt and water. Carboxylate salts are soluble in water. For this reason, carboxylic acids used in medication are usually in their soluble salt form instead of the acid itself. So this next part's important because this is how medications are made to be water soluble, so they can be in a pill that you can take, and then they can be soluble in your bloodstream eventually as well. So let's look at, for example, benzoic acid. Benzoic acid, again, is our benzene ring bonded to a carbon that's double bonded to oxygen that has an OH on it. So that C double bond O, OH, that's our carboxylic acid. And then we have NaOH, or we have our base. Okay, well, what's going to happen here is the H of our carboxylic acid is going to get together with our OH of our base to make water. That will leave our carboxylate ion. In this case, it's sodium benzoate. So the benzene with the COOH becomes COO minus. And then it's got an Na plus. And this carboxylate ion, I'm going to label it again. Here's our carboxylate ion. This carboxylate ion is an anion. And Na plus is the counter ion, or the cation, to the carboxylate anion. So we've got a cation and an anion. We have then a salt and water. So we have, this acid-base reaction. Acid and a base make a salt and water. This is our characteristic acid-base, neutralization type reaction. It's just that we need to be able to recognize this as a salt, where we have the carboxylate ion with some sort of counter positive cation, and then also producing water. So let's look at some examples. In this first example, we have CH3 bonded to a C, double bonded to an O, bonded to OH. What was that one? We wanted to recognize this particular carboxylic acid as actually acetic acid. So we've got acetic acid reacting with KOH plus KOH. Okay, so what's going to happen here? Well, the H of the carboxylic acid is going to get together with the OH of our base. Our potassium hydroxide is a strong base. And so when the OH and the H get together, that's going to make our water. And then we'll have to copy from acetic acid the beginning of its formula, the CH3, and then the C, double bonded to the O, bonded to the O, and that O is going to be negative. Instead of putting that last hydrogen on it, that was lost to water. Who's the counter ion to that carboxylate ion? Well, K plus is what's remaining. That would be our cation. So that is our salt. So we've got our carboxylic acid, reacts with our strong base, makes salt and water. Let's try one more example. This one's got HO with a C, double bonded to an O, bonded to CH2, bonded to CH2, bonded to a CH. That CH has an NH2 coming off of it, and then it also has a C, double bonded to O and bonded to OH. Whoa, we actually have a carboxylic acid on each end of the molecule. So both ends of the molecule have a carboxylic acid. And if you're really looking for your functional groups, we also had an NH2 in there or an amine. So let's just mark that and kind of file that away for later, like, oh gosh, there's an amine there. Now we're going to react that with sodium hydroxide or our strong base. So we've got our carboxylic acids. We're going to react that with our strong base. Since we have two carboxylic acids, we'll actually need two equivalents of our strong base if we were really keeping this balanced, because it can react with both sides of the molecule. So on both sides of the molecule, we want to go ahead and get that hydrogen of the acid together with an OH of our sodium hydroxide to make water molecules. In this case, it can make two water molecules. And then we'll end up with O minus on each side. So the first O minus is connected to a C, double bonded to an O. And then I'm going to copy the carbon chains in between. It was CH2, CH2, CH, and that CH had an NH2 on it, the amine. And then it was connected to a C that's double bonded to an O and also has an O minus on it. Who's the counter ion for these O minuses on these carboxylates? Well, Na plus. So let's squeeze in an Na plus on each side of the molecule. So two NAs, we make two waters. Because this molecule has two carboxylic acids, we really have kind of a doubling of everything we need for this. But we have a pattern here. We have acid, base, makes a salt, and water. It's just that here we have these carboxylate salts.